On August 23rd, 2023, at 6 minutes past 6 in the evening Indian Standard Time, a spacecraft called Vikram touched down on the surface of the moon at a latitude of 69 degrees south. The landing was the fourth soft landing on the moon by any nation in history. It was the first soft landing anywhere in the southern polar region of the moon, and it was, by a margin that the rest of this video will examine in detail, the cheapest soft lunar landing ever attempted. 3 facts about the mission frame the story. The first is the location. Every prior soft landing on the moon, by the United States, by the Soviet Union, by China, had occurred within about 45 degrees of the lunar equator. The Chandrayaan-3 landing site was more than 20 degrees further south than any of them. The reason for going that far south is not obvious from the engineering, which is harder at high latitudes than at low ones. The reason is scientific, and it traces back to a discovery made by an earlier Indian mission 15 years before. The second is the institution. The Indian Space Research Organization was founded in 1969, the same year the United States landed astronauts on the moon. For its first 3 decades, it was a small agency with a small budget, focused almost entirely on application satellites for communications, weather forecasting, and Earth observation. It did not undertake a deep space mission of any kind until 2008. 15 years after its first lunar mission, it accomplished a soft landing that 2 larger and more experienced agencies had failed to accomplish in the same year. The third is the cost. The total mission cost of Chandrayaan-3, as reported by ISRO, was approximately 615 crore rupees, or about 75 million US dollars at the exchange rate at the time of launch. For comparison, the production budget of the 2014 film Interstellar was approximately $165 million. The production budget of the 2015 film The Martian was approximately $108 million. The Chandrayaan-3 mission cost less to develop, build, launch, and operate than either of those 2 films cost to make. These 3 facts, the latitude, the institutional history, and the cost, are connected. The story of how they are connected is the story of how a country with a per capita income lower than the global average has become. Over the past 2 decades, one of the small number of nations capable of operating in deep space. We will take them in order. The Indian Space Research Organization was founded on August 15, 1969, 3 weeks after Apollo 11 returned from the moon. The juxtaposition of these 2 dates is the kind of thing that invites a particular kind of rhetorical use, and that use should be avoided. The founding of ISRO was not a response to Apollo. It was a response to a set of domestic Indian considerations that had been developing for nearly a decade and that had their origin in the work of a physicist named Vikram Sarabhai. Sarabhai is the person after whom the Chandrayaan-3 lander was named, and understanding what he believed about space programs is necessary to understanding what ISRO became. Sarabhai was educated at Cambridge in the 1940s, returned to India after independence, and founded the Physical Research Laboratory in Ahmedabad in 1947. By the early 1960s, he had become convinced that an Indian space program was not only possible but necessary, and his argument for this position was specific and unusual. He did not argue that India should pursue space exploration for reasons of national prestige, or as a demonstration of technological parity with the developed world. He argued instead that satellite-based communications, remote sensing, and weather forecasting offered the most efficient possible mechanism for delivering basic services to a country in which the majority of the population lived in villages that lacked terrestrial infrastructure. The argument is preserved in a statement Sarabhai made in 1969, which is worth quoting at length because it shaped the institutional character of ISRO for the next 50 years. There are some who question the relevance of space activities in a developing nation. To us, there is no ambiguity of purpose. We do not have the fantasy of competing with the economically advanced nations in the exploration of the moon or the planets or manned spaceflight. But we are convinced that if we are to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society. The phrase that matters in this passage is the application of advanced technologies to the real problems of man and society. Sarabhai's argument was that space technology was a means rather than an end. The end was the delivery of services. The means was whatever combination of orbital and terrestrial systems could deliver those services at the lowest cost. The argument was, in its underlying logic, an argument from cost effectiveness rather than from national prestige. This framing had consequences for the institutional culture of ISRO that persists today. The agency was structured from the beginning around the principle that missions had to be justified by their contribution to identifiable problems rather than by the technical achievement they represented. This is a different design philosophy from the one that shaped NASA during the Apollo era, which was structured around a specific prestige objective, landing a man on the moon, and which developed an institutional culture in which the technical achievement was its own justification. Neither philosophy is right or wrong. They are different, and the difference matters. ISRO's first 2 decades of operations were almost entirely devoted to application satellites. The Aryabhata satellite, launched in 1975 on a Soviet rocket, was an experimental platform for X-ray astronomy and ionospheric studies. The Bhaskara satellites, launched in 1979 and 1981, also on Soviet rockets, were the first Indian Earth observation satellites. The INSAT series, beginning in 1983, established a domestic telecommunications and weather forecasting capability that, by the early 1990s, was being used to deliver educational programming to villages across the country and to issue cyclone warnings that demonstrably reduce casualties from severe weather events. None of this is the kind of work that produces dramatic press coverage. The reduction in cyclone casualties on the eastern coast of India between the 1977 Andhra Pradesh cyclone, which killed approximately 10,000 people, and the 1990 Andhra Pradesh cyclone, which killed approximately 1,000 people, is partially attributable to better warning systems that depended on weather satellites that ISRO built and operated. This kind of attribution is hard to make precise and does not lend itself to anniversary coverage. But it is the work that ISRO was founded to do, and it is the work that ISRO did for its first 30 years. The launch vehicle program developed in parallel, and at substantial expense. India launched its first satellites on Soviet rockets because it did not yet have its own. The satellite launch vehicle, SLV-3, achieved its first successful orbital launch in 1980. The PSLV, Polar Satellite Launch Vehicle, achieved its first successful flight in 1994 and went on to become one of the most reliable medium-lift launch vehicles in the world, with a success rate that, by the 2000s, exceeded 95%. The GSLV, Geosynchronous Satellite Launch Vehicle, was a more difficult program that took longer to mature, but by the late 2000s, it had become reliable enough to support deep space missions. The relevant point about the launch vehicle program is that it was developed by a country that did not have the metallurgical industry, the propellant chemistry expertise, or the electronics manufacturing base that the original spacefaring nations possessed. The development required parallel investment in all of these supporting industries. The cost of this parallel investment is not captured in any specific mission budget because it was spread across the entire industrial base of the country over several decades. When the headline figure for Chandrayaan 3 is given as $75 million, that figure does not include any allocation for the launch vehicle development that made the mission possible, because the launch vehicle was developed under separate programs and amortized across many missions. It was not until 2003 that the Indian government, under Prime Minister Atal Bihari Vajpayee, authorized ISRO to undertake its first lunar mission. The decision was contested within the Indian policy community. The argument against was the argument Sarabhai had made decades earlier, that a developing nation's space program should be focused on applications rather than exploration. The argument in favor was that the technical capability ISRO had developed by 2003 had reached a point at which lunar exploration would not divert significant resources from the applications programs, and that the strategic and scientific value of a lunar mission justified the expenditure. The argument in favor prevailed. The first mission, Chandrayaan-1, launched on October 22, 2008. It was an orbital mission only. It carried an impactor that struck the lunar surface near the South Pole, but the impact was for the purpose of kicking up surface material for spectroscopic analysis rather than for landing in any operational sense. The mission's significance was not the impactor, but one of the instruments on the orbiter, and that significance is the subject of Section 3. Chandrayaan-1 was followed by Mangalyaan, the Mars orbiter mission, which launched in November 2013 and entered Mars orbit in September 2014. The mission is the closest analog to Chandrayaan-3 in terms of what it demonstrated about ISRO's institutional capability, and it deserves to be treated with care. Mangalyaan achieved Mars orbit insertion on its first attempt. This is unusual. Of the previous attempts at Mars orbit insertion by other agencies across the United States, the Soviet Union, the European Space Agency, and Japan, the majority had failed on first attempt, often catastrophically. The Soviet Mars program had attempted Mars orbit insertion 7 times before achieving a partial success. The Japanese Nozomi mission, launched in 1998, failed to enter Mars orbit in 2003 after a 5-year journey. The European Beagle 2 lander, deployed from the Mars Express orbiter in 2003, failed on landing. ISRO's first attempt success placed India in a category that, prior to 2014, contained no other agency. The technical reason this is hard is that Mars orbit insertion is a single burn that must be executed at a specific moment, at a specific magnitude, with the spacecraft on the far side of Mars from Earth and therefore out of direct communication. The burn must be planned in advance, executed autonomously, and verified after the fact. There is no opportunity to correct it in real time. The first attempt success rate across the history of Mars exploration has been approximately 40%. ISRO's mission succeeded the first time with a spacecraft that cost approximately $74 million to develop and launch. The cost figure is the one that drew the most attention in the international press, and the comparison most often made, that Mangalyaan cost less than the production budget of the film Gravity, which was released the same month Mangalyaan launched, became the kind of comparison that defined the agency's international reputation through the mid-2000s. The comparison was accurate but partial. It did not capture the institutional context that made the cost achievable, and it created an expectation in subsequent coverage that Indian missions would always cost an order of magnitude less than comparable Western missions. This expectation has shaped the coverage of every Indian deep space mission since, and it is worth examining carefully because the underlying economics are real but more complicated than the headline numbers suggest. The cost differential between Indian and Western space missions is partially an artifact of accounting practices. ISRO's headline figures do not include allocations for prior infrastructure investment, launch vehicle development amortization, or full burdening of personnel costs against indirect overheads. Western agencies, particularly NASA and ESA, use accounting practices that do include such allocations. A directly comparable accounting would narrow the gap. But the gap does not disappear after accounting adjustments. The remaining differential is not magical. It is the consequence of three factors: substantially lower labor costs in India, a domestic supply chain for many spacecraft components that does not require purchasing from high-cost Western or Japanese vendors, and an institutional culture that treats budget as a primary design constraint, rather than as a parameter to be optimized after technical decisions have been made. The first two factors will narrow over time as the Indian economy develops. The third factor is the one that is most specific to ISRO and most worth understanding. Mangalyaan demonstrated that ISRO could plan and execute a deep space mission to another planet at a cost comparable to its Earth orbit missions. Saryam mission operated in Mars orbit for nearly 8 years, substantially longer than its planned operational life of 6 months, and returned a body of data on the Martian atmosphere, the methane question in particular, that contributed to the international understanding of Mars during a period when several other Mars missions were also operating. By the time Chandrayaan-2 launched in 2019, ISRO had established a track record across application satellites, planetary orbital missions, and launch vehicle development that placed it among the small group of agencies capable of operating in deep space at all. The remaining gap was the soft landing gap. Orbital missions are difficult. Landing missions are harder, by a margin that is not always appreciated by audiences whose mental model of space exploration is shaped by the Apollo era. The first soft lunar landing was not achieved by the Soviet Union until 1966 after a sequence of failed attempts. The first American soft landing followed a few months later. The Chinese first soft landing was in 2013. No agency outside this group had landed softly on the moon prior to 2023. That this is the gap Chandrayaan-3 closed is the engineering question we will return to in Section 4. The question of why Chandrayaan-3 landed at 69 degrees south rather than at one of the lower latitude sites used by every prior lunar lander is a scientific question, and the answer to it depends on a discovery made 15 years before the landing by an instrument that was not Indian. The Chandrayaan-1 orbiter, which launched in October 2008, carried 11 instruments. 5 of them were Indian. The remaining 6 were contributed by foreign agencies: NASA, the European Space Agency, and the Bulgarian Academy of Sciences. The Indian government's policy on international payloads on Indian missions has been consistent across decades. Foreign instruments are welcome on Indian spacecraft when the science they conduct is of mutual interest and when the contribution does not compromise Indian control of the mission. This policy distinguishes ISRO from several other agencies that have been more restrictive about foreign payloads, and it has been the basis for a substantial portion of the international scientific cooperation that ISRO has conducted. One of the NASA instruments on Chandrayaan-1 was the Moon Mineralogy Mapper, an imaging spectrometer designed to map the composition of the lunar surface at a resolution of approximately 140 meters per pixel. The instrument was led by Carla Peters of Brown University. Its scientific objective was to characterize the mineralogy of the lunar crust across the entire lunar surface, with particular attention to the polar regions, which had been less thoroughly mapped by prior missions. The instrument operated for approximately 10 months before the Chandrayaan-1 mission ended prematurely due to a thermal control failure. During those 10 months, it returned a body of data that, when analyzed in the months following the mission's end, contained a finding that changed what was known about the moon. The finding was water. The spectroscopic signature of hydroxyl and water molecules at wavelengths around 2.8 to 3.0 microns was present across substantial portions of the lunar surface, with concentrations increasing toward the poles. The signature was strongest at high latitudes, particularly in the permanently shadowed regions of the polar craters, where surface temperatures never rise above approximately negative 170 degrees Celsius, and where any water ice deposited by past cometary impacts or by other mechanisms would be stable for billions of years. The finding was published in Science in September 2009. It was independently confirmed by reanalysis of data from other missions. The Deep Impact spacecraft and the Cassini mission, both of which had made distant observations of the moon while traveling to other targets. And the convergence of three independent datasets eliminated the possibility that the result was an artifact of any single instrument. The discovery was significant in a way that requires careful statement. It was not the first suggestion that there might be water on the moon. Earlier missions, particularly the Lunar Prospector mission in 1998, had returned data consistent with the presence of hydrogen at the lunar poles, which was interpreted by some researchers as possible evidence of water ice. But the Lunar Prospector data was indirect, and the interpretation was contested. The Moon Mineralogy Mapper data was direct spectroscopic evidence, and the interpretation was not significantly contested. It changed what the moon was understood to be. The implications were substantial. If water exists at the lunar poles in concentrations sufficient to be extracted, it can be used as drinking water for human occupants of a lunar base. It can be electrolyzed into hydrogen and oxygen, which can be used as rocket propellant. The presence of usable water on the moon transforms the economics of lunar operations because the alternative, transporting water from Earth, costs on the order of $1 million per liter when fully burdened against launch costs. A lunar base supplied by lunar water is feasible. A lunar base supplied by Earth water is not. The Moon Mineralogy Mapper discovery was the proximate cause of a substantial reorientation of international lunar exploration toward the polar regions. NASA's Lunar Reconnaissance Orbiter, which had launched in 2009, intensified its observations of the polar regions over the following decade. The LCROSS mission, also in 2009, deliberately crashed a spent rocket stage into a permanently shadowed crater near the South Pole and observed the resulting impact plume, which contained spectroscopic signatures of water vapor. The Chinese Chang'e program reoriented its later missions toward higher latitudes. The Russian Luna 25 mission, when it was eventually launched in 2023, targeted the South Polar region. The American CLPS program, which contracts commercial landers to deliver payloads to the lunar surface, has prioritized polar targets. The reorientation toward the polar regions was the context in which Chandrayaan-2 and Chandrayaan-3 were designed. The Indian government's decision to follow Chandrayaan-1 with a lander mission and to target the lander at the South Polar region rather than at a more accessible low-latitude site was a decision that followed directly from the M3 discovery. The agency that had carried the instrument that made the discovery would now place a vehicle in the region the discovery had made important. This is the sequence that matters for understanding why 69 degrees south was the target. The latitude was not chosen because it was difficult. It was chosen because it was where the science was. The difficulty of operating at that latitude, the colder temperatures, the lower solar elevation angles, the more challenging terrain, was a cost that the mission accepted in order to be in the right place. A note on what 69 degrees south actually means in terms of where the lander sits. The landing site is on the rim of a region between the craters Manzinus C and Simpelius N, at an elevation that receives sunlight during the lunar day, but is in close proximity to permanently shadowed regions of nearby craters. The lander itself did not enter a permanently shadowed region. The temperatures in those regions are too cold for the lander's systems to operate, but it landed close enough to such regions that future missions, equipped with rovers capable of surviving longer cold periods or designed specifically to enter shadowed terrain, could use the Chandrayaan-3 landing site as a reference point and starting location. This is the strategic logic of the site selection. Chandrayaan-3 was not the mission that would extract lunar water. It was the mission that would demonstrate that the region where lunar water exists could be landed on, that vehicles could operate there, and that subsequent missions could be planned around the geography of the area with the confidence that comes from in situ data rather than from orbital remote sensing alone. The mission was a reconnaissance in the strict military sense, establishing presence in a region of strategic importance from which subsequent operations could proceed. The science instruments on the lander and the rover were modest by comparison to the scientific instruments on the larger and more expensive lunar missions of other nations. The lander carried 4 instruments measuring near-surface plasma density, thermal conductivity of the lunar regolith, seismic activity, and a Langmuir probe for ionospheric studies. The rover carried 2 instruments for elemental composition analysis. None of these instruments were designed to detect water directly. The detection of water at the landing site was not the mission's primary objective. The mission's primary objective was to demonstrate the capability to land at this latitude. The science was secondary to the demonstration, and this was a deliberate choice rather than a limitation. The location itself was the contribution. The science explains where the lander was sent. The engineering explains how it got there, and the engineering story begins with a failure. Chandrayaan-3 succeeded on the first attempt at its specific objective. It was not, however, India's first attempt at a lunar landing. The Chandrayaan-2 mission, launched in July 2019, had attempted to land in approximately the same region of the Moon, with a lander of similar mass and similar configuration, and had failed. The Chandrayaan-2 mission consisted of an orbiter, a lander, and a rover. The orbiter component succeeded fully, entering lunar orbit in August 2019 and beginning a planned 7-year mission of high-resolution mapping and remote sensing that continues today. The orbiter remains operational more than 6 years after its arrival, and it has returned a substantial body of science, including detailed synthetic aperture radar observations of polar ice deposits that have refined the understanding of where water is concentrated within permanently shadowed regions. The lander and the rover, however, did not succeed. The lander, also called Vikram, separated from the orbiter on September 2, 2019. The descent began on September 6th. The lander completed the first phases of the descent successfully, including the rough braking phase that brings the vehicle from orbital velocity down to approximately 350 meters per second. The failure occurred during the subsequent phase, called the fine braking phase, at an altitude of approximately 7.4 kilometers above the surface. The lander deviated from its planned trajectory, attempted to correct, and exceeded the limits of its corrective control. It impacted the lunar surface at a velocity greater than the lander was designed to survive, approximately 500 kilometers from its intended landing site. The post-failure investigation, conducted by ISRO and reviewed by external experts, identified the cause of the failure as a combination of factors rather than a single point of failure. The lander's main engines had produced thrusts slightly higher than the planned profile during the rough braking phase, which left the vehicle higher and faster than the descent algorithm expected at the start of the fine braking phase. The algorithm attempted to compensate, but the parameters governing the compensation had been set with margins that did not accommodate the magnitude of the deviation. The software did exactly what it was designed to do, and what it was designed to do was not enough. This is the kind of failure that is common in spacecraft development, and that is, in retrospect, identifiable as a consequence of testing limitations rather than design oversight. The descent algorithm had been tested extensively in simulation. It had not been tested against the specific combination of off-nominal conditions that occurred during the actual descent, because that combination had not been anticipated as a likely failure mode. The test campaign had been thorough by the standards of pre-mission planning. It had not been exhaustive, and exhaustive testing of all possible off-nominal combinations is not feasible for any spacecraft mission. The Indian government's response to the failure was not to terminate the program. It was to authorize a follow-on mission specifically designed to address the failure modes identified in the investigation. This response is worth pausing on because it reflects a specific institutional disposition that distinguishes ISRO from some other space agencies that have responded to high-profile failures by canceling the affected program or by undertaking such substantial redesigns that the follow-on mission was effectively a new development effort. The Chandrayaan-3 mission was scoped narrowly. It would use the same orbiter, which was already operating, and would replace the lander and rover with redesigned versions specifically targeted at the failure modes of the prior mission. The redesign was extensive. The lander's structure was strengthened to accommodate higher landing velocities, providing margin against terminal descent deviations of the kind that had occurred in 2019. The engine configuration was modified, with the lander now carrying 4 corner engines plus a central engine rather than the 5-engine configuration of the prior mission to provide more redundant thrust control. The descent algorithm was rewritten with substantially wider margins for off-nominal conditions, and the test campaign for the new algorithm specifically included the failure scenario of the prior mission as a test case. The landing zone was expanded from a small target area to a much larger one, on the assumption that giving the vehicle more room to land would absorb a wider range of terminal trajectory errors. The fuel capacity was increased, allowing the lander to conduct more aggressive corrective maneuvers during descent if needed. The legs were redesigned to accommodate harder landings. The sensors were upgraded, including the addition of a higher resolution hazard detection camera system that would allow the lander to identify safe landing sites during the terminal descent phase rather than relying on pre-mission targeting alone. The development period from the September 2019 failure to the July 2023 launch was approximately 4 years. This is a fast development cycle for a follow-on spacecraft mission. The factors that made it possible were the availability of substantial heritage hardware. The orbiter and the launch vehicle were already operational, and the focused scope of the redesign. ISRO was not developing a new mission concept. It was fixing a specific failure on an otherwise validated architecture. The mission was approved in 2020. The launch was originally planned for 2021 and was delayed by approximately 2 years due to a combination of the COVID-19 pandemic, which disrupted ISRO's operations as it disrupted operations at every space agency, and the need for additional testing of the redesigned components. The launch eventually occurred on July 14, 2023, on an LVM-3 launch vehicle from the Satish Dhawan Space Center on the eastern coast of India. ISRO's public framing of the Chandrayaan-2 mission throughout this period was that it had been approximately 95% successful, counting the orbiter component as a success and treating the lander failure as a partial loss. This framing was met with some criticism in the international space community as rhetorical overreach, and the criticism has merit. A soft landing either succeeds or it does not, and a lander that impacts the surface at lethal velocity has not been 95% successful regardless of how the mission's other components performed. But the framing also reflects something accurate about the mission architecture, which was that the orbiter and the lander had been designed to perform substantially independent scientific functions, and the orbiter's success was not contingent on the lander's success. The post-failure period for Chandrayaan-2 was, in retrospect, the period during which the institutional capability for Chandrayaan-3 was developed. The failure investigation produced not only a list of corrective actions, but a set of testing methodologies that had not been used in the prior development cycle. The team that had developed the failed lander developed the successor. The institutional memory of what had gone wrong was preserved and acted on. This is the way space programs typically learn, from failures that are diagnosed accurately and addressed specifically. And it is the way ISRO learned in this case. The Chandrayaan-3 spacecraft was launched on July 14, 2023 on an LVM-3 launch vehicle. The launch placed the spacecraft into a highly elliptical Earth orbit. Over the following 2 weeks, the spacecraft conducted a series of orbit-raising maneuvers, each one extending its apogee further from Earth, using a technique called orbit pumping that takes longer than a direct translunar injection but requires substantially less propellant. The technique is one ISRO had developed and refined across multiple missions, and it is one of the specific contributions to the cost economics of Indian deep space missions. The trade of time against propellant is a trade that ISRO has consistently made in favor of propellant savings. The spacecraft entered lunar orbit on August 5th, after a journey of approximately 3 weeks. It then conducted a series of lunar orbit-lowering maneuvers, gradually reducing its altitude and circularizing its orbit. The lander module was separated from the propulsion module on August 17th. The propulsion module remained in lunar orbit conducting auxiliary observations. The lander conducted 2 further orbital maneuvers to lower its periapsis to approximately 25 kilometers, the altitude from which the powered descent would begin. The powered descent was scheduled to begin at 5:45 p.m. Indian Standard Time on August 23, 2023. At 5:44 p.m. IST, the lander began its preparation sequence. The vehicle reoriented itself with the engines pointed in the direction of motion, opposite to its orbital velocity vector, so that engine thrust would decelerate the vehicle rather than accelerate it. The 4 corner engines and the central engine ignited at 5:45 p.m. The lander was at an altitude of approximately 30 kilometers above the lunar surface and moving at approximately 1.68 kilometers per second relative to the surface, which is the orbital velocity at that altitude. The rough braking phase lasted approximately 11 minutes. During this phase, the lander's engines fired continuously at high thrust, reducing the vehicle's velocity from orbital speed to approximately 358 meters per second. The altitude decreased from 30 kilometers to 7.4 kilometers. This altitude was the failure inflection point of the Chandrayaan-2 descent, the altitude at which the prior lander had begun to deviate from its planned trajectory 4 years earlier, and the safe completion of this phase was the first major test of the Chandrayaan-3 redesign. At 5:56 p.m., the lander completed the rough braking phase within its planned trajectory parameters. The attitude hold phase that followed lasted approximately 10 seconds, during which the vehicle reoriented from its braking attitude to a near vertical attitude in preparation for the final descent phase. At approximately 5:58 p.m., the fine braking phase began. The fine braking phase brought the lander from 7.4 kilometers altitude to approximately 800 meters altitude. During this phase, the lander's hazard detection camera was actively imaging the surface below, comparing what it saw against preloaded maps of the landing region and identifying potential hazards, boulders, slopes, craters that would make the planned landing site unsafe. The lander had the capability to autonomously divert to an alternate landing site within a defined search radius if the primary site was determined to be hazardous. At approximately 800 meters altitude, the lander conducted a hazard avoidance maneuver. The specifics of this maneuver have not been published in detail, but the available information indicates that the lander identified the planned landing site as containing surface features that exceeded the safety thresholds in its onboard algorithms, and it diverted to a nearby alternate location. The maneuver was conducted autonomously. There was no opportunity for human intervention. The signal delay between Earth and the Moon at this distance is approximately 1.3 seconds one way, which means any ground command would have arrived too late to affect the lander's behavior during a phase of flight that was being executed in real time at a rate of meters per second. The hazard avoidance capability was one of the specific upgrades from Chandrayaan-2. The prior mission had targeted a smaller, more precisely defined landing site. The Chandrayaan-3 mission was designed with the assumption that the landing site would need to be selected during the descent itself, based on real-time imaging, and with sufficient propellant reserves to support the lateral movement required for autonomous diversion. The capability worked. The terminal descent began at approximately 150 meters altitude. The lander was at this point descending nearly vertically at low velocity, with the central engine providing fine thrust control while the corner engines maintained attitude. The descent continued for approximately 75 seconds, with the lander's velocity reducing to a few meters per second as it approached the surface. Touchdown occurred at 6:04 p.m. Indian Standard Time on August 23, 2023. The confirmation of touchdown was delayed by approximately 15 seconds, which was the time required for the signal indicating successful landing to travel from the Moon to Earth and to be processed at ISRO's mission control in Bengaluru. The video coverage of mission control from that 15-second interval, which was broadcast live, shows the room in a state of suspended attention. Engineers watching their screens, the principal investigators standing at the front of the room, the silence that occupies a control room when the spacecraft is past the point at which any intervention is possible, and the team is waiting only to learn whether the work of the prior years has succeeded. The signal arrived. The room broke. There is a particular quality to the celebration of engineers who have spent 4 years preparing for 15 seconds of action, and the celebration in Bengaluru that evening had it. It was not the celebration of a victory. It was the celebration of a relief. The relief of a team that had carried the failure of 2019 for 4 years and had finally set it down. The Prime Minister, who was attending the BRICS summit in Johannesburg, appeared by video link to congratulate the team. The lander deployed its ramp. The Pragyan rover rolled onto the lunar surface a few hours later. The mission's primary objective, demonstrating soft landing capability in the south polar region of the Moon, had been achieved. The lander and the rover operated on the lunar surface for 1 lunar day, approximately 14 Earth days. They returned data on the near-surface plasma environment, the thermal conductivity of the regolith, the elemental composition of the surface materials at the landing site, and the seismic activity of the region. None of these data sets were transformative for lunar science individually, but they were the first in situ measurements ever made in the South Polar region, and they established baseline values against which future missions to the region will be calibrated. The lander and rover entered hibernation as the lunar night began on September 4th. The expectation was that they would not survive the lunar night, during which temperatures in the region fall to approximately negative 200 degrees Celsius for periods of approximately 14 Earth days. The vehicles had not been designed for survival of these conditions. The design choice to omit survival heating was a cost optimization that the mission planners had made deliberately, in the knowledge that survival would be uncertain and that the mission's primary objectives would be achieved within the first lunar day regardless. ISRO attempted to re-establish contact with the lander and the rover after the lunar dawn of September 22nd. No signal was received. The vehicles had not survived. This outcome was within the range of pre-mission expectations and was not treated as a mission failure, because the mission success criteria had been defined with respect to the first lunar day rather than to any subsequent period of operation. The $75 million headline figure for Chandrayaan-3 is the number that drew the most international attention to the mission, and it is the number that deserves the most careful examination, because the comparisons it invites are partly accurate and partly misleading. The accurate part is straightforward. The mission did cost approximately what ISRO has stated it cost. The figure of 615 crore rupees is the appropriated budget for the mission as approved by the Indian government, and the actual expenditure was within that envelope. The mission delivered a soft landing on the moon at the South Polar region. The cost per outcome ratio is real. The partly misleading part is that the headline figure is not directly comparable to the headline figures of Western lunar missions. The differences are of three kinds. The first is accounting. ISRO's mission budgets are reported as the marginal cost of the specific mission, the spending attributable to the mission's development, hardware, launch, and operations during its primary phase. They do not include allocations for the infrastructure that supported the mission, including the launch vehicle development that was amortized across many missions, the deep space tracking network that was developed for prior missions, and the personnel costs that are partially absorbed into ISRO's general operating budget rather than charged against specific missions. NASA's mission cost figures, by contrast, are typically reported as the fully burdened cost, including allocations for these supporting investments. A direct comparison of headline figures overstates the differential. The second is labor. The cost of skilled engineering labor in India is substantially lower than the cost of equivalent labor in the United States, Europe, or Japan. This is a real factor, and it is not eliminated by accounting normalization. A senior spacecraft engineer in India earns approximately 1/5 to 1/4 of what an equivalent engineer earns in the United States. The development of a spacecraft is labor-intensive in a way that substantially reflects engineer hours, and the labor cost differential flows through to the total cost. The third is supply chain. India has developed, over decades of consistent investment, a domestic capability to manufacture most of the components that go into its spacecraft. The components are not always at the performance level of the best Western or Japanese components, but they are adequate for the mission requirements, and they are available at a fraction of the cost. The mission planners have, consistently across multiple missions, made the trade of accepting lower component performance in exchange for substantially lower component cost. And the trade has consistently worked at the system level. The remaining differential, after all three of these factors are accounted for, is the institutional one. ISRO treats budget as a primary design constraint. The mission is scoped to fit within the budget rather than scoped first and then priced. The descent algorithm uses propellant carefully because propellant is expensive and the launch vehicle's capacity is limited. The science instruments are modest because instruments are expensive. The lander does not include survival heating for the lunar night because heating is expensive, and the mission's primary objectives can be achieved without it. Each individual decision is small. The accumulated effect across thousands of decisions is the cost differential. The differential cannot be explained away entirely on accounting grounds. The remaining differential is not magical. It is the consequence of choices that other agencies could, in principle, also make, and that some other agencies, notably the Chinese space program and the new commercial American lunar landers operating under the CLPS program, are beginning to make. The cost parameters that the major Cold War space agencies have treated as fixed are not, in fact, fixed. They reflect institutional habits more than they reflect the underlying economics of space activity. This is the most important strategic implication of the Chandrayaan-3 mission, and it is the implication that the agencies most committed to the prior cost parameters are most reluctant to acknowledge. The strategic context of the mission extends beyond cost. India's success at landing in the south polar region of the Moon occurred in the same month that the Russian Luna 25 mission failed at the same task. Luna 25 had been launched on August 10, 2023, with the same target region as Chandrayaan-3 and with the explicit objective of arriving before the Indian mission. The Russian lander entered lunar orbit successfully on August 16th. It attempted a pre-landing orbit adjustment on August 19th. The maneuver failed and the spacecraft impacted the lunar surface. The Luna 25 failure was the first Russian lunar mission since 1976. The gap of 47 years between Luna 24 and Luna 25 reflects the broader trajectory of the Russian space program, which has experienced substantial institutional decline since the dissolution of the Soviet Union. The failure was not a single isolated event, but the visible manifestation of a long process of capability loss. The contrast with the Indian mission, which succeeded at the same task 4 days later, drew international attention to the relative trajectories of the two programs. Institutions can do this in both directions. The Russian space program has spent 4 decades losing the capability that the Indian space program has spent 4 decades acquiring. The international response to the Chandrayaan-3 success was substantial. NASA's administrator publicly congratulated ISRO. The European Space Agency, which had contributed tracking support to the mission, issued a statement of congratulation. The Chinese Space Agency, which has its own active lunar program and which has historically been competitive with ISRO, also issued a statement. The accumulated effect of these responses was a recognition that India had joined a small group of nations capable of soft landing on the Moon, and that the group's economic profile had changed. There is a domestic political dimension to the achievement. The landing site has been officially designated Shiv Shakti Point. August 23rd has been declared National Space Day. The Prime Minister appeared by video during the descent and at multiple subsequent ceremonies marking the achievement. These facts are part of the record of the mission. They do not affect the engineering or the scientific significance. The trajectory of ISRO's program in the years following Chandrayaan-3 includes several missions that build on the mission's accomplishments. The Aditya L1 mission, launched in September 2023, has reached the L1 Lagrange point and is conducting solar observations from there. Station keeping at L1 is a non-trivial accomplishment and places India in another small group of agencies capable of operating deep space observatories at libration points. The Gaganyaan crewed spaceflight program, which has been in development for several years, is targeting a first crewed flight later this decade. The Chandrayaan-4 mission, currently in development, will attempt a sample return from the lunar surface, a capability that no agency outside the original spacefaring nations has yet demonstrated. The Bharatiya Antariksh Station, India's planned space station, has been announced for the 2030s. Whether these subsequent missions will succeed, as Chandrayaan-3 succeeded, is not yet known. What can be said with confidence is that they are being pursued by an agency that has, in the past 2 decades, accumulated a track record of measured ambition and consistent execution that places it in a different category than it occupied at the beginning of this century. The trajectory is upward. The institutional culture is intact. The cost discipline that produced the $75 million lunar landing is being preserved as the agency takes on more ambitious targets. The 3 facts that opened this video. The first was the latitude. Chandrayaan-3 landed at 69 degrees south, in a region of the moon that had never been landed on before, because that region is where lunar water is concentrated, and lunar water is the resource that will determine whether human activity on the moon is economically feasible at all. The choice of landing site was a strategic positioning. The second was the institution. ISRO accomplished what it accomplished because of a 50-year institutional history of treating space technology as a means rather than an end, of investing consistently across decades, and of building a domestic capability rather than purchasing capability from abroad. The institution was built deliberately over a long period with a clear set of principles, and the principles produced the result. The third was the cost. The mission cost less than 2 recent Hollywood films about space exploration. This is the fact that drew international attention, and it is the fact that has the most strategic implications, because it suggests that the cost parameters that the major spacefaring nations have treated as fixed are not in fact fixed. They reflect institutional habits more than they reflect the underlying economics of space activity. An agency that treats budget as a primary design constraint, that builds a domestic supply chain, that scopes its missions narrowly and executes them carefully, can do what the agencies of the Cold War period could do, at a fraction of the cost the Cold War agencies considered necessary. This is the most consequential thing that has happened in space exploration in the past decade. It is more consequential than any individual mission because it changes the set of nations that can plausibly conduct space exploration at all. On August 23, 2023, at 6 minutes past 6 in the evening Indian Standard Time, a spacecraft called Vikram touched down on the surface of the moon at a latitude of 69 degrees south. It was the 4th soft landing on the moon by any nation in history. It was the first soft landing anywhere in the southern polar region of the moon. It was the cheapest soft lunar landing ever attempted. And it was, in all 3 of these respects, the beginning of something rather than the end of it.